Thank you. Okay, sorry, I'm back. Like I said, I have opened the Google Classroom for you to be able to access this material. It's like there's no chat. Okay, it's coming up. Okay, it's coming up. Okay, so the code, like I said, it is ooyomi@gmail.com. Ooyomi, OOWOYOMI, OOWOYOMI @gmail.com. OOWOYOMI @gmail.com. And the code for the Google Classroom is DOF 5 PBIV. I'll repeat that again. DOF 5 PBIV. Again, DOF 5 PBIV. That is the passcode for the Google Classroom. So if you go there, you'll be able to access all the slides, the lecture notes. Yes, DOF 5 PB, not PP, please. Iomide Babs is PB, 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 correct? PBIV. Now, in small letter, all through, not capital, small letter, please, small letter. Okay, please. Daramola Michael changes to small letter so I can know is DOF 5 PBIV. That's the passcode for the Google Classroom for you to access all the slides, all the lecture notes. In fact, for the slide, I also have I've done how do I put it now, an audio overlay on it so that once you open it on the system, you can even hear me explaining each of the slide. Okay, so please, that's correct. Correct, absolutely correct. DOF 5 PBIV, correct. And the email is OOWOYOMI. OOWOYOMI. Okay, the code I just gave now is not attendance code, is code for you to be able to access the lecture material on Google Classroom. PB, Taura Dynasty. It is PB, the first one. Peter Bible. Okay. Peter Balogun. Small letter. Yes. Adeyemi, small letter. I think some people are missing things up here. The code I just gave now is not for attendance. It's for you to be able to access the. Maybe you should have done that at the end of the whole they are confused. Don't be confused. I mean, don't be confused. The code I just gave now is not for attendance. I said for you to be able to access the entire slide, the material for this lecture, I have put it on Google Classroom. Now, to access Google Classroom, you will need that code that I just dictated now, DOF 55PBIV. And somebody is asking, yes, Tioluwanimi Oluwasindara, owoyomi@gmail.com. You are correct. That is, just go to Gmail, just go to Gmail, then you can look at the app. Google Classroom is an app on Gmail, and of course, it's attached to. So once you open owoyomi@gmail.com, you will see the Google Classroom. You enter the code, and you'll be good to go. Okay. All right. So that is all how far I can go for today. Quite unfortunate that I could not write anything on the board for you. It's quite unfortunate, but it is what it is. Like I always tell my students, you are not going to buy a 500 naira calculator and be looking for second function. Oyinbo. So we hope that government will fund university appropriately, and all these little issue will have been dealt with if we have enough fund to fund the system. But it's okay. The university is making efforts. Don't worry. All this thing will be hopefully by next semester. It's going to be better than this. University is working hard on it to make sure that you are comfortable with this mode of lecture delivery. Okay, so thank you very much. Now, for our attendance now. Thank you, Samuel Abidoye. I like that response of yours, because some students are asking, what is Google Classroom? I like your response. You will respond that if they have attended the ICT training, they will have heard about Google Classroom. This means that a number of them just did not bother to come for various training as provided by the university, and now you are running into issue. But of course, don't worry, you can always interact with those who are smart enough to attend the ICT training. All right. The next code for attendance now. The next code for attendance is 5DRJ4. 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 Now, for the attendance, everything is in capital. For the attendance, everything is in capital. 5DRJ4. Thank you. 5DRJ4. Thank you very much. That's the second attendance code. I will give the last attendance code in the next 3 minutes, so I can enter this second one. The first one is AF4V8. You already have that, AF4V8. The second one is 5DRJ4. 5DRJ4. All right, 5DR. Adeleke Abiodun Omotayo, you're asking for the first code now, when the code was given over 30 minutes ago. Well done. Okay. Abigail Ajayi, I can understand your dilemma. A number of you got admitted after the ICT training. It's okay. Sorry about it. It's okay. Don't worry. You will blend. You will adapt. Don't worry. Just that's all you need. Just adapt, and you'll be good to go. Yes, 5DR. J4, not JRO. Inioluwa Modupe is 5DR J4, not JR. And finally, for today, the attendance code is 9 LURW. 9 LURW. 9 Lanre Unicorn. Lanre Unicorn. Regina Wosilat. 9 good. 9 LURW. 9 LURW. Thank you very much. I want to wish you the very best in the tests and, of course, in the exam. Peace out. Thank you. But I guess I'm done. Everything should be settled today, this is sure, right? We settled today. It's essential stuff. That's time at least. The issue is that it just this everything has been going smoothly. Fantastic. No, because of this no, it was a free something. Oh my gosh. And sometimes some of them some software but then we should make it a university to invest in some of the software again. Considering the volume of you can't there's no way it's what you pay for, that's what you get. That's try and when you look at the acceptance fee of 10,000. So no.
Okay. Oh, okay. Good. Okay. Good morning, everyone. We're sorry for a little delay. This is Physics 101, and we'll continue where we stopped on Monday. That's the center of mass and linear momentum. Center of mass and linear momentum. Please, I want us to do a little preview of what we did yesterday. Yesterday, we look at some of this outline. Oh, sorry, on Monday, we look at some of this outline. We talk about the center of mass, Newton's second law. Look at some of this outline. We talk about the center of mass. Newton's second law for a system of particles, linear momentum. We look at the linear momentum of a system of a particle. There we look at collision and impulse, conservation of linear momentum, momentum and kinetic energy in collision. Today we'll continue with inelastic collision in one dimension and elastic collision in one dimension. Then we'll look at a system with a varying mass. Example is a rocket. So those are the overview of what we did yesterday. For those of us that are not around on Monday, we talk about rigid body. Sorry, sir. It's cutting out some of the. Okay. So those are the things that we look at yesterday. Linear momentum of a system of particles. And we look at the force as it relates to momentum. The rate of change of momentum with respect to time give us the force. Collision and impulse. That's what we defined yesterday. Conservation of linear momentum. There we said for an isolated system, the energy is conserved. And if the energy is conserved, then the change in linear momentum with respect to time is what? Zero. And if that's zero, which means all external forces acting on the system is zero. And that's what we refer to as the law of conservation of linear momentum. Momentum and kinetic energy in collision. We said if the total kinetic energy of the system remains unchanged after collision, then the energy is conserved and collision is known as elastic collision. However, in some cases, energy may change from one form to the other, which means kinetic energy of the system may not be conserved. And provided it's an isolated system, the momentum is still conserved, and we refer to it as inelastic collision. Yesterday, we look at Monday we look at inelastic collision, and we look at the velocity of the center of mass for a closed and isolated system. We look at collision in one dimension, elastic collision in one dimension, in which you have a rigid body and a moving object and a moving body, the two of them coming together. And that's where we stop on Monday. So we'll continue from there today. So the class, please, the first attendance code is PWD 4Y. PWD 4Y. That's the first antenna code. PWD for Y. I want a reaction. You said the slide is not clear. If it's not clear, then it's from your own end. Attendance is not opening. Then maybe you need to look at your network. Is PP as in power, W as in work, D as in done, 4, and Y as in you. Yeah. But they say Yusufu. That's right. Pastor Yusufu, no. It's P, not E. PWD4Y. Oluwa Bori Adeyemi, that's right. Deborah along with me is P, not B. P as in power. Okay. Ayomi, Deborah, no. Okay. Now we can continue with the lecture. The code is P as in power, W as in work, D as in done, 4, and Y as in you. So we can continue. And from that equation that we got for the initial velocity and the final velocity of the first moving object and the final velocity of the second moving object. And from there, it shows that if they have equal mass, if M1 and M2 are equal, what happens to your V1F? M1 minus M2 will be 0. Okay? So V1F will be 0. If they have equal mass, so V2 final will just be the same thing as V1 initial. So which means the first object stop. Then for a massive target, there is where your target, which is M2, is greater than M1. Now, the first object just bounced back and speed mostly unchanged. So for massive projectile, your initial velocity, the velocity of the first object, the final velocity of the first object will always almost equal to the velocity of the initial velocity of the first object. And the final velocity of the second object will just be approximately 2 times the initial velocity of the first object. So the first object keeps going, the targets fly forward at twice its speed. For a target that is also moving, assuming the second target is not stationary, that's what we have. Your V1F will be given at that equation, and your V2F will be given as that equation. So V2F will be 2M1 M all over M1 plus M2 V1 initial plus M2 minus M1 all over M1 plus M2 V2 initial, provided that the two objects are moving. Now let's look at collision in 2 dimensions. Now, if it's in 2 dimensions, which means, from the diagram that we'll see on this side, the moving object has direction in both Y and X axis. For example, let's say M1 is moving towards M2. And by the time it gets to M2, the two objects will scatter along SY, and that's what we have. So the V1F will be going towards the negative of X, towards the negative of Y, and the V2F will be going towards the negative, towards the positive of Y. So applying the conservation of momentum along each axis, and that's what you do. Normally you have two equations, one that has to do with momentum, and you apply the conservation of energy for elastic collision. For example, if you have a stationary target, that is your M2 is not moving, your M1 has a component along X alone and is moving with a velocity of V1. So you found out that your M1, V1 initial, will be the same thing when you balance the force. M1, V1 final, the cosine of the angle it makes plus M2, V2 final, the cosine of the second angle. Mind you that though M1 is moving along the negative y-axis, but the cosine is positive within that quadrant. You know, between 0 and 90, tan, sine, and cosine are positive. Okay? And the second quadrant, you have sine alone being positive, the third, tan, and the last being the cosine. Then along y, the initial moment will be 0 because as it were, there was no moment. But then by the time they collided, there's a movement along both y, positive y, and negative y. Now you find out that because the first mass M1 is along the negative y, sign is negative there. And that's why we have minus M1, V1 final, the sine of the theta, the angle there, plus M2, V2 final, the sine of the angle there. And when you look at the energy is given as half M1 V1 I, which is same thing as half M2 V2 X, V1 to F. Now, mind you, it's for a stationary object. If it's not stationary, then we'll consider the M1, the initial energy of the M1. And lastly, under this section, we'll look at system with varying mass. Example is a rocket and the exhaust product form an isolated system. Now this is what we have. By the initial time of your rocket, it has both the weight of the rocket plus the fuel. But as the rocket is moving, certain masses are being ejected. And that's what propels the rocket to move forward. So you find out that if you look at it as a closed system, the momentum is conserved, which means the initial momentum will be the same thing as the final momentum. Now, the initial momentum we can easily write, and that one we can give as your mass, that's total mass, times the velocity. But then the final momentum now breaks down into so many components. The dm is the mass that is being ejected, and the velocity of that mass is u. That mass can be in form of the fuel being consumed, okay? Plus the mass plus the m. You know that as a rocket is moving, the velocity will increase. So you have your velocity plus change in velocity. So we can simplify using the relative speed, which is u, and we'll define it as your u same thing as the initial velocity plus change in velocity minus the relative velocity. Therefore, the first rocket equation is defined as r multiplied by the relative velocity, which is same thing as the mass, which is ma, where your r is the mass rate of fuel consumption, and the left side of the equation is the thrust, T. So derive the velocity change for a given consumption of fuel, and we use that one as the second equation. And this is what we arrive at. Your final velocity minus the initial velocity is same thing as a relative velocity lane of the initial mass all over the final mass. Let's consider the mass energy equivalent. The conservation of mass states that in any physical or chemical process, mass is neither created nor destroyed. From what we knew from our secondary school, matter cannot be created nor destroyed. And the mass energy relation was developed by Einstein in 1905, and it gave us the relationship between the energy and the mass, where your AR is the energy equivalent of mass, that's the rest mass energy, and C at the speed of light, which is taken as 3 times 10 raised to approximately 3 times 10 raised to power 8, and M is the mass of the object. From that equation, A equals mc squared, we can now determine the rest energy or 1 kilogram of any substance. So that will be mass times c squared. If the mass is 1 kilogram times square root of the velocity, and that's the same thing as 9 times 10 raised to the power 16 joule, which is constant for any substance of 1 kg. And from there also, our change in mass, we can relate it as change in energy all over c squared. So that brings us to the N of the center of mass. Briefly, we'll go into the next slide, which is rotation. I'll take part of it, and my colleague will finish the rest with you. Sir, let me look at the second one. It's okay. So while we are waiting for the slides to be loaded, can we have the next attendance code? I have CT CA9. The next attendance code, that's the second attendance code. C as in city, T. Oh, beautiful. Beautiful. Okay. Yeah, we'll solve question by God's grace tomorrow. I'll bring some of the questions that we'll look at together. That's okay. That's CTA9. That's beautiful. Okay. The second code, CTA9, that's beautiful. Emmanuel, that's beautiful. So just hold on as we load the second slide. This 2 of 2. Let's do this. Good. I see. So we are welcome back. I hope all of us have gotten the second code. The first code asked from your colleague. The lecture start by 9. The lecture start by 9. Okay. Okay. For the sake of those of us that have problem with our network, the first code is PWD. P as in power, W as in work. Yes. Yes. Adejuwan, Deborah. Yes. We are solving problem tomorrow by God's grace. Okay. The first code is PWD 4Y. P as in power. Oh, Oluwaye Ford. That's good. That's the first code. Okay. And the second code is CTC A9. Okay. The slide, don't worry, they will get the PDF across to you by God's grace latest by Friday. Okay. Mr. Adeshope will get it across to you. Mary Akia is CTC A9. Okay. Nifemi Abiodun, that's fine. Okay. So let's continue with the second one. Now we want to look at the center of rotation of mass and linear momentum. I'm going to consider just 4 aspects of it. First aspect of it, I want to look at the overview, rotational variables, rotation with constant angular acceleration, and how to relate the linear and angular variables together. In your first 2 lectures, I know you have been given the normal equation of motion based on the first law, second law, and third law for a linear. You have relationship between distance and acceleration. You have relationship between the initial velocity and the velocity with respect to time. So that will also solve for rotation and see how the linear that you've learned is related to the angular acceleration and velocity. Now, rotations, as it were, is a fundamental concept linking natural phenomena with engineering system. For example, we all knew that the heart wherein we reside do spin. Okay? We know that machines and industrial processes, we have so many things that spin in it. Also, we know that when we rotate, we can convert one energy to the other. For example, those of us that ride bicycle, we can convert the mechanical to another. Then now also help us to look at how do we improve efficiency? How do we stabilize? And how do we produce? And whether you like it or not, a proper understanding of it makes life better and will help us to advance technologically. I'm going to limit myself to some of the implications of rotation. Number one is a physical and engineering implication of rotation. You want to look at forces associated with rotation. There you'll be talking about centrifugal and centripetal effects, because these are the things that you need to consider, or else a rotating body may spin out of control. Then we'll look at torque and the angular momentum. Also, we use them in control and stability. For example, the gyroscopic effects, and that's what we apply in stabilization in ship, aircraft, satellite, and smartphone. Variation and fatigue, and in metals failure as a result of aging. So you find out that the rotational concept affects every days of life. For example, your normal vehicle that you ride on, what you have is that the tire kept on rotating, okay? And that's why you are able to move from one point to the other. So the first thing we'll look at is the rotational variables. What are the variables? In considering the variables, we'll consider the motion of rotation. And we find out that in considering the motion of rotation, the same law that applies to the linear motion also is applicable to the angular motion. But then there are some new quantities that we need to consider, or we use to express them. In terms of the F, your force, we'll consider torque. In terms of your mass, we'll consider rotational inertia. So those are the things that we equate to each other. And you find out that when you equate it, mass to inertia, torque to force, then you can apply the first, second, and third law of motion to angular motion. Now, when we talk about a rigid body, a body is rigid when it rotates together as a unit. That is, they are locked together. Okay. For example, this phone now, if I rotate it, it's not rotating differently. Okay. It's locked together. It's locked together. So, and when we rotate it, we'll look at it that we rotate it about a fixed axis. That is, it's rotated about a fixed axis. In considering our fixed axis, there are certain things that we will not consider. We will not consider sun. Where the layers of gas rotate separately. So a physical eyes is as if sun is rotating along as a rigid body. But when you move closely, all the layers of gases that surrounding the sun rotate separately. Our consideration will also exclude rolling bowling ball. In that case, two motions occur. You have the rotational motion and the linear motion occurring simultaneously. The fixed axis is what we refer to as the axis of rotation. Look at that figure down, figure 2 and figure 3. Sorry, the second one is supposed to be figure 3. The angular position of this line is taken relative to a fixed direction. Now look at it. Here is the reference point, the reference line, and this reference line is a part of the body, and found that it's perpendicular to the rotational axis. And the reference line, we use it to measure the rotation of the body relative to a fixed direction. And the second diagram depicts the direction of the motion. For this one, the body has rotated counterclockwise. We know the clock moves from left to right, and the counter of it will be from right to left. Now the dot there means that the rotation axis is towards you. So the measurement is done in radians. Okay, the angle by which it rotates is done in radians, and you find out that it doesn't have any units. Okay, it's a dimensionless. It's same thing as x all over r, where your x is the distance move along the arc. This is the distance moves along the arc, and your r is the radius. And that gives us equation 10.1. And one revolution is equivalent to 360 degrees, which is same thing as 2 pi radian. And the angular displacement is a change in the angle, just like we have the linear displacement. Okay, so from the linear motion or translational motion, you have the distance, which is equivalent to the angle theta in angular motion. We don't change the distance. It's same thing as final distance minus initial distance. The same thing happens here. The final angle minus initial angle. And the convention that we use is that any angular displacement in the counterclockwise direction is assumed positive. Because when we are measuring angle, we always move in counterclockwise. We start from 0 positive axis down till when we make 360 degrees. And the one that moves in the clockwise direction is negative. Just like we have the linear displacement, we have the linear velocity. Also, we have the angular velocity. The angular velocity will just be changing theta with respect to time. But the average angular velocity will be the angular displacement during a time interval, and that will be theta 2 minus theta 1 all over T2 minus T1. And that's change in angular displacement all over change in time. And also our acceleration, which is instantaneous, we say the angular velocity is given as that, and the angular velocity is denoted as W, or in some they call it omega. Your linear velocity is V. Your omega W is the angular velocity, and instantaneous angular velocity, you take the limit as your T change in time turn to 0, and with that you have equation 6. Note that if the body is rigid, then all the above equation holds for all points on the body. And the magnitude of the angular velocity is same thing as the angular speed. You know, velocity is a vector quantity. So the figure shows the value of calculated average angular velocity. Say it changes from theta 1 to theta 2. And changing is theta theta. And it's equal to the angular displacement of the body during itself during this time interval. The same time, we know that our acceleration from linear displacement is velocity over time. Likewise, angular acceleration is angular velocity all over time. Therefore, the average angular acceleration is same thing as a change in angular velocity all over change in time. And that's what we have as equation 7. Now, when you talk about instantaneous angular velocity, what we just do is to take the limit as theta 3 turns to 0. And like I said earlier, if you talk of rigid body, all this equation holds for all points of the body. We can use the right-hand rule to determine the direction, the angular velocity, and the angular acceleration, just like a linear velocity and linear acceleration, can be written as a vector form. If the body rotates around the vector, then the vector points along the axis of rotation. However, note that angular displacement are not vector, because the order of rotation matter. If it moves towards the clockwise, it has a negative. If you move towards the anti-clockwise, it has a positive. So the order of rotation matters for rotation around different axes. Therefore, it's not a vector. The rotation with constant angular acceleration. So the same equation holds just for linear acceleration. And it's stated here from your first lecture or second lecture, you have the linear equation for velocity that relates the initial velocity and the final velocity and time and acceleration together. And the equivalent is what we have as equation 12. We have the distance, change in distance, in linear, being linked with the change in velocity, with velocity and time and acceleration. And we have the equivalent as equation 13. Likewise, the initial velocity and the final velocity has a relationship with the acceleration and distance. And equivalent is equation 14. We relate the angular velocity with the angular displacement and angular acceleration. Equation 217 talks about the change in distance and how it relates to the change in velocity over time. And that is equation 15. And equation 18 gives us that change in distance related to change in velocity with time and acceleration. And the equivalent is equation 16, which relates the change in acceleration is change in angular distance with change in velocity and acceleration. Now, let's look at how we'll relate the linear and angular variables together. The common factor between them is r. That's the radius or the perpendicular distance from the rotational axis. Note that your theta is in radian, where your x is in meter. So the s is related to theta r. Your speed v is related to omega, that's the angular speed, times r. And the period in radian is same as 2 pi all over r. Also, the acceleration, the linear acceleration is related to angular acceleration with a factor of r. That we say in equation 22. And we can write the radial acceleration in terms of angular velocity. We know that's v squared all over r, and that's omega square r. And that brings me to the end of the lecture today. Please, let's write down the last code of the lecture. By God's grace, tomorrow we'll go back to the chapter 9 and try and take 2 or 3 working examples. Basically, you know, our test is Alidea Wrestling. That's a 10 version. So we'll pick some of the work example there and see how we'll solve it. So the code, the third code is X as in Xian, XLT 3G, X as in X-ray rather, X as in X-ray, Oh, beautiful. Christopher Mamilari. Yeah, SLT3G. Okay. SL, okay, that's good. Oduayo, Ige. Midnight, okay. Esther Yakubu, that's good. SLT3G. Omishake, Joseph Akonde, okay. Okay, okay. The second code, why are you asking for the second code? Maybe you go through your chat, which means you came late. Okay, goodbye. I'll see you tomorrow.
Yes. Good morning. This morning, we want to continue from where we stopped. We started this aspect on Monday, and as part of my revision, I would like to pick these last few slides before we continue from where we stopped. Work done in ideal gas said whenever a gas is allowed to expand from a specific volume Vi to Vf, where your I is the initial, and V of F is the final volume, where we keep the temperature constant. Such a process at constant temperature is called an isothermal expansion. And the reverse is called isothermal compression. And like I said, you have to note that the two basic terms here is the expansion and the compression. So this term determines the application of the volume you want to change. So that must be followed when we get to the application area, that is the calculation. That is very important. Now the next slide relates the expression or the general equation. We have discussed P as your pressure. P will be equals to nRT over V, where N is your number of mole, R is the gas constant, T is the temperature, and V is the volume. And that has been assigned as equation 13. So I am assuming also that you are familiar with the change of subject of formula. So everybody can do that for me now, so that your equation 13 can be converted to equation 14. So that your equation 13 can be converted to 14. Therefore, PV will be equals to nRT. PV equals nRT. How that's taken? So we can easily move to the next slide. Where the work done by an ideal gas during an isothermal expansion now becomes W, representing your work done. So we want to integrate from volume initial to final volume Vf for the pressure with relevance to the change in volume. And that becomes your equation 15. Now recall from your equation 13 and 14, we said PV is equal to nRT. Substitute that into that expression 15. So the work done now becomes the integral from initial to final nRT over V, where n remains your number of moles, R is the Gauss constant. In any exam, the value of the constant will be given to you. The temperature of the gas is T capital and V is the volume. Here we have also assumed that you have gone through simple integration and differentiation in your O-level classes. And like I said in the general class, it is very important for people in this field or area to know simple integration and differentiation, so that when I input the value, then you'll be able to solve the problem. Everybody should be able to know what we mean by work done from this equation 16. And like I said in the general class, you may be tested at any time. Now it's difficult for me to know who is attending my class physically. I see you on the road along Lagri Road and give you a question like I used to tell you in the class. But just take note of all this equation. So it is now easier for us to move to the next slide. The next slide, for an isothermal expansion, T, which is the temperature, is constant now. That's why the word isothermal is important. Hence, you can see the equation changes. The work done is now nRT, integral from initial to final volume for dV over V. And that stands out as your equation 17. Now take down these notes. The work done, particularly for a constant temperature, the work done, particularly for a constant temperature, shows that it combines the relationship of the temperature and the number of mole for the ratio of volume expansion. So take that as another important point for you before we go ahead with the slide. I believe that is taken. It's now easier for us to move to the next slide. In this next slide, the work done can also be transformed. And each equation is very important, and you have to take note of the equation. The work done in this case is the product of the number of moles with the gas constant and the change in temperature of the gas, multiplied by the ln of V. Ln there represents the length, which you are familiar with from mathematics. And that changes must take place between the initial and the final volume. So that can easily be substituted for in your general mathematics in case we are given the question. Now that is taken. The next slide. We want to evaluate the expression in brackets. And in order to use the relationship, it's like saying ln of A minus ln B, which is a fraction of A over B for that ln. That's why I put that in brackets. So it will be easier for you to make a direct substitution in case a specific value is supplied or given to you. And mind you, like I said in the general class, this class or course, this aspect is like mathematics. So you have to be good in mathematics, or you go and revise your mathematics notes. All the aspect of logarithm, aspect of evaluations of log, and so on and so forth, relevant to this topic. You have to go and revise that so that it will be easier for you to compute or calculate so easily. And like also advised in the class, you can link up with your friend who knows better. That's the essence of your class, forming a tutorial class within yourself. So that somebody who knows better can share with somebody who is following up. That's the essence of getting better and performing better in the class. So take note of this expression. They are very important. Next slide. Therefore, this is for ideal gas isothermal process. Thus, if the volume of gas is constant, then work done is 0. So you can take note of that equation also, which is your equation 20, like we said. Then I want you to put this note briefly as I also dictate. You follow up to this particular equation so that it helps you to understand better, one, the equation, then number two, how to apply the equation. So note that work done is equivalent to the energy required for the process of the gas evaluation. That is why the work done and energy, the unit, you notice that they are in joule. An expression of the energy released by a particular volume of gas at a particular time expresses your work done. So all other factors are constant factors. Then in any case, the number of mole, like we earlier discussed, will be given in any calculation. So it's a matter of simple substitution. And this will help me to remind you that during your exam and test, you have to come along with your calculator. But this is purely science, mathematics. So don't borrow calculator only during the exam. You must be familiar with the use of your own calculator. Very important. So take note of that. We can now move to the next slide. But if the volume changes while the pressure is held constant, then the equation change so that you have your work done equals to final volume minus initial volume will give you the product of the change in volume and the pressure. So take note of that. equation, you can see behind the bracket something is missing out, and that's your pressure. So pressure will be given to you in the exam on any test if you have to calculate the work done, or sometimes if the initial volume is to be found or determined, it simply means the final volume will be given and the pressure of the gas. So easily we can calculate the work done. I believe that is taken. Now, take this code for your attendance. QN H6Z. QN H6Z. Q in capital, N in capital, H in capital, 6, then Z in capital. I hope that is taken. Okay. Now we can go ahead. I want to give you this example so you can try it now. A cylinder contains 12 liters of oxygen. At 20 degrees Celsius, not 200, and 15 atmosphere. The temperature is raised to 35 degrees Celsius. And the volume reduces to 8.5 liters. That's full stop. What is the final pressure of the gas in the atmosphere? In bracket, assume the gas is ideal. So applying your equation there, PV is equal to nRT for initial and PV for nRT for final. That's F represents your final. I want you to follow along that as I'm a bit slow with this calculation so that you try to do it yourself. Before I open up to the next slide. So you just substitute the value directly and come up with the answer. Anyway, if we have done that, we can move to the next slide. So that's the attempt or the solution. Initial temperature there, Ti, is 273 plus 20, which is the temperature given to you. you know you must convert to Kelvin. So in order to convert temperature to Kelvin, you have to add 273. And that gives you 293. And final temperature, TF, is 273 plus 35. And that gives you 308. So we are looking for final pressure. So make that the subject of the formula. And then substitute. Are you trying to do that quickly? Because this is an area where I want you to participate. Okay? All right, if you have done your substitution correctly, then the next slide will show. The final pressure will now be 15 multiplied by 308 and by 12 divided by 293 times 8.5, and that gives you 22.3 atmosphere. And that's how to solve problems in case you are given another value. In another question, you may be given the final and asked to calculate the initial. All you need to do first is to apply what you call change of subject of formula in your mathematics idea. And then you get the problem solved. So I want to assume that you are familiar with this simple calculation. We can move to the next slide, right? Now this is example 2. 1 mole oxygen, assumed to be an ideal gas. Sorry, that is gas, not gas. Expand at a constant temperature of 310 Kelvin from an initial volume of 12 liters to a final volume of 19 liters. So how much work is done by the gas during the expansion? So this is another aspect where I'm expecting your trials using the same equation as we have done in example 1. Meaning that at any instance of this meeting, you get a jotter by your side. So a minute, almost 30 seconds will be given to you to follow along by solving the same problems. And that gives you the better understanding of what you are supposed to do. So apply your equation and let's see your results. Okay. From the application of the equation, we can look at the next slide. The work done, nRT ln VF over VI, where I is the initial volume and VF is the final volume. You can now see the reason why the understanding of the mathematics is important. You need to know how to relate it with physics Now I want to assume you are familiar and you have written down this equation. It is now easier for us to make substitution. Substituting this, you can see clearly you have 1 multiplied by 3.8 times 310 ln of 19/12. So you must be familiar with the use of your calculator, not because of this class, but because of your test and exam. Like I said in the general class, don't love borrowing calculator. Get your own calculator. If you don't have, contact your local government chairman, like I said. They'll provide for you. So your answer must be converted to kilojoule. That's why you see kJ there. Because in the option, sometimes to be given in the test or exam, the option may be in kilojoule or mega. So you must know the simple conversion from joule, microjoule, kilojoule, and so on and so forth. Other units, unit is part of exam. So you must understand the unit so clearly. So I want to believe that is taken. We can now move to the next slide. Now we want to look at the pressure, temperature, and root mean square speed. That RMS represents the root mean square speed. Now take down the following apart from this equation. The root mean square speed simply represents the speed that you put in bracket, the average of the speed the gas molecule experience when pressure is exerted on the container at constant temperature. So 3 variables are important in this case. The volume which we are dealing with, the temperature, and the pressure. In fact, these are the 3 variables that determines the study or the measurement of gas and the content in any container. Once it is gaseous state, then these 3 variables must be considered: the pressure, the temperature, and the volume. So now the equation 22 will now be applicable in this case. The equation 22, pressure is equal to N small letter represent your number of moles. M there now represent the mass, volume. RMS below, which is a subtract, is the root mean square. But don't forget that the entire expression is squared. So if you have to make any substitution, you put it in bracket in your calculation, then you square it. That equation 22 is very important. Now, before we go ahead, I want to give you another code. The code is C2UMY, all in capital. C2UMY, C capital, U capital, M capital, Y capital. Good. So I want to assume you are following. You want to go ahead to the next slide. V RMS is the root mean square speed of the molecules. For M in this expression, equation 23 represents your molar mass. That is actually is a mass in a unit of mathematics, but we are concerned about the molecular value of the mass involved as a gas. That's why you refer to it as molar mass. So otherwise it would have been just any ordinary mass. And V is the volume. So the new equation now emerges. Our VRMS now becomes the square root of 3RT over M. Now in this case, your R is your gas constant, 8.31. You're familiar with that. T will be temperature that will be given to you in any test or exam. Temperature of the gas. Molar mass will also be specified. Then you also note this from equation 23. If you are given the root mean square speed, which is your VRMS, and you have to calculate the temperature of the gas, then it will take you the time now to make T capital in that equation 23 the subject of the formula. That's why I said the key application of this topic is the change of subject of formula in your mathematics. So everybody should be able to do that. That means you square both sides, and the square root on the second side will be removed. That's the first step. The third step now shows that VRMS is square. You are now left with 3RMT over M. You cannot make T the subject of the formula. So Vm equals to 3RT. In other words, your T will now become VRMS M divided by 3R. So make your substitution and you get the correct answer. So like I said in the general class, if there's any problem which is personal about understanding the equation, inform your friend. If your friend cannot answer correctly, that's why the class is open to the class rep. The class rep knows how to get in contact with me, like I told you generally in the class. So you can come along with your class rep or course rep. That will be sorted out. How that equation 23 is now clear. But the general problem, as noted in the past, is the change of subject of formula to most of the students. So you have to go back to that. So we can move to the next slide. The average translational kinetic energy per molecule in an ideal gas is given by this expression. And very simple because we assume you are familiar with this equation even from secondary school. It is only in the area of application that you have a little difference. And what is the application? It's just a simple substitution of the value given to you. So your M will be the mass of the gas, the ideal gas, and the velocity, which is associated with the speed of motion. I know in this case we are connected with velocity, not speed per se, because we are talking of energy. So the speed, RMS speed, when it is square for the value given to you, will now give you the kinetic energy. Now, another situation may come where the mass will not be given to you in the calculation. In that case, you use the second expression. That is, your kinetic energy becomes 3/2 kT, where K will be a Boltzmann constant, as was generally explained in the class. You just made the substitution. So your average kinetic energy can now be 3/2 multiplied by Boltzmann constant K and the temperature change within the ideal gas. Very simple to do. So take some calculation in your past questions and notes and textbook and solve the problem as been given to you. I want to assume that that slide is taken. So we can move to the next slide. This is possible in a situation where Avogadro's number is given in any calculation. So it is easier to now calculate the constant yourself before you apply it to the equation, to the problem given to you. Note that R is your gas constant. So K can be calculated directly using your calculator. Note that the value of the power of anything in your bracket is very important. If it carries minus of the power, then you have to take note of the changes that will take place in your fraction according to your mathematical expression. So this is where mathematics is totally connected with physics. So you have to take note of that. So you can easily calculate this expression. So we can move to another topic or subtopic, which is the mean free path. Mean free path, a typical molecule is assumed to move through the gas, changing both speed and direction abruptly as it collides elastically with other molecules. Now, as you go ahead, I want you to put it on your jotter. Like I said, you should get your jotter side by your side, because this is the summary of what you're supposed to know. But in order to amplify or get it better, I will dictate this, which are basic points for you to know when it comes to mean free path. The keyword free is what we need in this subtopic. So it is assumed that any matter that shows free motion will generate what we call collisions. Because it's not just one matter particles. There may be more or many within the container. So that boundary creates what we call collision. And so each particle matter takes to its direction. So the rate of collision is considered by the speed and the closeness of each matter particle to each other. And this is also this has been explained to you in your O-level class. We're only trying to build up on it. So understanding the direction and collision will give you the relationship between movement of molecules in a container. And so without this understanding, you can't talk about expansion, because these are the basic principles underlining expansion of gases in a container. Then it also explains when a container is sealed or opened. It also explains the type of gases involved. So these are the basic things you need to understand under the main free path. Now I can go ahead. Between collisions, the molecules move in a straight line at constant speed. So, like I used to tell you in the general class, I can ask which of the following statement is not correct. So you should be able to pick which statement is not correct about mean free path and collisions of particles or molecules of gases. The next key point here is this random motion is best described as the mean free path. And that is always represented with lambda. That symbol you see there is called lambda. And we have decided to choose this as a symbol because from the beginning of discussion of gases, lambda has been known to be the general representation, so we cannot change it at this point. So take note, the free mean path will be represented with lambda. So let lambda represent the average distance traversed by a molecule between collisions. And this is where another statement has to be taken. That is, put it down somewhere for you to note and remember. When you are going through other textbooks, these are the key words or key statements to be emphasized. Collisions occur when two or more molecules or matters are enclosed. So take note of that. And the rate of collision is subject to the thermal energy within the contents of the motion of the molecules. That is, if the molecule is so enclosed that the space between the motions is reduced, the collision will be higher. Another factor that increases collision is the thermal or heat energy generated in the course of motion. So take note of all this. This can come out in form of simple question that which of the following is the general factors, or which one is not correct about the factors determining the motion of molecules in the course of collision. So lambda at any time will represent that average distance. And so the path between two molecules, or the gap, is otherwise known as that distance. And so it can be easily measured. So we can now move to the next slide. So this key statement is very important. Mean free path varies inversely with the number of molecules per unit volume. And that's your N over V. Mean free path varies inversely with the density of molecules. Take note of all these points. The larger the number of molecules per unit volume, the more the rate of collision. Then 4 point, the larger the density of molecules, the smaller the mean free path. So how do we mean by that? So you have to take down this note along this keyword or key statement. In other words, the density of molecules is inversely proportional to the mean free path. So that can come out as any other question which is brought out of this general statement. The same way when you say the mean free path, which is your lambda, is inversely proportional with the number of molecules. So number of molecules indirectly speaks about the density, because number of molecules in a particular volume, unit volume, is the density. So we are still saying the same thing, but in another way. So take note of that as we move to the next slide. The average distance traversed vary inversely with the size of the molecules. Next point, the larger the molecules, the smaller the mean free path. The larger the molecules, the smaller the mean free path. Next point, the mean free path also vary inversely as the square of the molecular diameter. So sometimes lambda, which is your mean free path, can be proportional to d squared. So d, if you are given any calculation, represent your diameter, you just substitute the value, and k will be your constant. So somebody can now say lambda is equal to kd squared. So can easily calculate whichever is unknown in the expression. So there's no doubt there will be calculation in your question, not just a direct statement. So you have to take note of all this. Then notes to be taken now, I'll give you another statement. The size of a molecule. The size of a molecule is very important when it comes to the mean free path. When it comes to the mean free path. In other words, the path taken by the molecules in terms of numbers, path taken by the molecule in terms of numbers is directly related to the mean free path. So take note of that as we move on. Therefore, the general expression for the mean free path becomes lambda equals 1 over square root of 2 pi d square n over v. That I will tell you should be taken as equation 27. you have to understand what each symbol represents and how it is placed. There are so many ways by which you can make the student to understand or confuse the student in quotes, because I want to put it as a question. Look at where that square root stops. So if I want to make a multiple choice option, I can extend that square root to up to d squared, but it's not correct. So you should be able to identify the actual equation for lambda, which is your mean free path. What does D represent? What does N represent? What does V represent? The how is it placed? Is it N over V or V over N? These are the way to confuse students better. But you are the one that will stick to the correct equation given to you in your notes. So the correct equation, therefore, is exactly written in that form of equation 27. The square root will only stop at 2, not on pi, not on d squared, and not on the entire expression at the denominator. So that indirectly I've given you answer to some of the possible questions that may come up. Then finally, on this equation 27, every one of you should be able to make D the subject of the expression, which is the next thing I'm expecting you to do now, before I show you what the answer will look like. In 1 or less than 1 minute, what is your D in relation to lambda and V, which is your volume? So make D the subject of the formula quickly and call it equation 27b. Call it equation 27b. I'll give you the opportunity to take the last code. Okay. Okay. Now take the next code. WG 8P8. WG, W capital G capital 8P capital 8 again. Yes, I can see some of you. That's good. Okay. With this, I think this would be a convenient time to stop for today. on Friday, we take our time. Submit your attendance. I can already see the multiple number of response. Good. All right. So we'll meet on Friday. Thank you.
Hello, class. Thank you for joining the lecture today. And mind you, we are meeting again on Friday, the same time, and it is going to be virtual as well. And also remember, our continuous assessment is still February 7, 2026. Please, if you have any complaint, any comment, you are free to see me in my office. I'll be waiting for you to give you reply. Thank you.